Sensors for hands.
Oh,
Yeah.
Like the Tesla, by like weight too, so you can do like the weights you put on your wrist, you just put it on the steering wheel.
that's wild. They have weight sensors in their steering wheel.
It's like going by like touch, so like you just figured out like the wrist weights, you just put them on the steering wheel.
Next, they'll have
But it
to.
also has a camera though.
Oh my gosh! You know that technology on your phone screen that like uses the electrical signal or like water content of your finger? Like that's why if you have a glove on, you can't swipe on your screen because it can't sense your finger. But if you splash it with water, it will move stuff on your screen because it's getting the electrical signal or whatever. I don't know how it works really, but they could put that on the steering wheel. Oh, but then you couldn't use like gloves when you're driving. Anyways,
Yeah.
let's solve this structure. If you guys remember, at the start of the week, I gave you an IR spectrum for a compound with the chemical formula C4H8O, and we did the calculation. What did we find the degrees of unsaturation to be? 1 degree of unsaturation. And how many different structural isomers did we think of? 1, 3, 18. Individual structural isomers, we said that that degree of unsaturation could be a ring. And how many different rings could it be? A lot of different rings. Could be a 3-membered ring, 3-membered carbon ring, 3-membered epoxide ring. Could be a 4-membered carbon ring, 4-membered ether ring. Could be a 5-membered ether ring. Could be a 6-membered ether ring with 2 ethers in it. Not to mention the degree of unsaturation could be pi bonds. Could be a CO double bond. Could be a CC single bond. It could be a CC single bond that's directly connected to an ether, a CC double bond that's far away from an ether. And with the CO double bonds, we said it could be an aldehyde, a ketone, a carboxylic acid, an ester. A very small a very small chemical formula. I've got a typo up there, don't I? That's not the chemical formula. It's 2 oxygens. Very small chemical formula, very large number of structural isomers possible. So then we looked at the IR, and the IR spectrum told us there is a CO double bond, which means the degree of unsaturation is not due to a carbon-carbon double bond. There are no CC double bonds. There were no sp2ch bonds. We saw evidence of the CO double bond. We saw no evidence of the OH stretch for a carboxylic acid or an alcohol, which tells me that we're dealing with either an ester, a ketone, or an aldehyde. We also looked at the IR and said that there is no CH of the aldehyde. So we knew that the structural isomer possibilities that had aldehydes were out, and we were down to these 3 structural isomers. 2 of them are esters, but you'll notice their carbon chains are different. Here there's 1 carbon next to the carbonyl, and 2 carbons after the ester linkage. And then they flip. 2 carbons after the carbonyl, 1 carbon after the ester linkage. And we have the option of a ketone with an ether. Because this oxygen is not bonded to the carbonyl carbon, it's not an ester. This is a ketone and ether. And because the CO double bond was in a very comparable place, we're not sure whether that CO double bond belongs to a ketone or an ester. So we moved on to its NMR. And we covered 4 very important things about understanding how to interpret the NMR. 1, individual hydrogens don't give their own signals necessarily, but unique sets of hydrogens produce their signals. So hydrogens that are in the same exact chemical environment. And we didn't even get into the more in-depth aspects like diastereotopic hydrogens. hydrogens that are on the same carbon, but if they were a chiral center, they would have different experiences in the molecule. Too in depth. Not what we're looking at. Instead, we're just saying sets of hydrogens. So a CH3, that's one set of hydrogen. A CH2, one set of hydrogen. And sometimes symmetry gives us equivalent sets that are on opposite sides of the molecule, but they're the same set. And then those signals that those sets of hydrogens produce, they show up with a specific chemical shift. Sometimes helps us understand the functionality. They show up with a specific integration. I'll give you those integrations as some number of H, but active gives you those integrations as the lines showing the change in area. And the last part is the splitting pattern. Now this is an NMR example with a very clean splitting pattern. Those of you that took the lab this week or have lab tonight, you looked at NMR spectra with very clean splitting patterns. But a lot of the experimental spectra that I give you on unit tests and exams, their splitting patterns are messy, they're challenging to read. The splitting pattern is actually where a lot of the structural information is stored, because it tells you how many neighboring hydrogens that signal has. A CH3 group with 2 neighboring hydrogens gets split into 3 peaks with its signal. So there's a lot of information there. That information is not always easy to pull out. Here, we can see it really, really clearly. So, how many unique sets of hydrogens in this molecule? Three unique sets of hydrogens. One hydrogen produces a signal here, around 4.25. One produces a signal here, around 2.0. One produces a signal here, around 1.25 ppm. So, 3 unique signals. What about my 3 possible structures? How many unique signals will they make? 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so the number of signals doesn't narrow it down. Next, what does the chemical shift tell me about these groups? Well, this chemical shift region here between 0.5 and 2, according to our correlation table, that indicates things that are mostly just alkane, things that are not functional group adjacent. All right, that would be considered an alkane signal. It's adjacent to a CH2 group, whereas the CH2 is adjacent to an oxygen, and this CH3 is adjacent to a carbonyl. So this would be one signal in the alkane region. This would be one signal in the alkane region. This is functional group adjacent, so is this, and so is this. So this molecule is actually starting to look less likely due to the chemical shifts. Let's see if we can come up with other reasons to rule it out. Integrations. Okay, it's not given on here, but the integrations from left to right, and maybe I'll sketch this out just so we have it. I've got a quartet that integrates to 2H. I've got a singlet that integrates to 3H. And then I've got a triplet that integrates to 3H. So, not only do I have 3 unique signals, but those signals need to have integration of 3H, 3H, 2H. 3H, 3H, 2H, 3H, 3H, sorry, 3, 2, 3, 3, 2, 3. So, all 3 of the structures, again, could have those integrations, unfortunately. Next, let's look at the splitting patterns. I need to have 2 hydrogens that have how many neighbors? 3 neighbors. Peaks equals neighbors plus 1. So peaks minus 1 tells me how many neighbors. 4 peaks minus 1, 3 neighbors. How do you get a CH2 group, let me show that a little bit different colors. How do I get a CH2 group? And I'm predicting that because the integration is 2H. That has 3 neighbors. Well, I could have a CH3 on one side, and I don't know what's on the other side, but given that its chemical shift is past 4, this is probably a functional group. And given that it only has 3 neighbors, whatever this group is doesn't have any hydrogens on it. Or I could have a CH2 group that has a CH2 on one side and a CH on the other side. That would also give me 3 neighbors. Well, if I look at my 3 possibilities, I never see a CH2 group that has 1 H on one side and 2 H's on the other. But I do have 2 structures where a CH2 has 3 hydrogens on the other side. So either of these structures agrees with this signal. This structure actually does not. This CH2 group has no neighbors. That CH2 group should be a singlet. So it's not that bottom structure. Okay, moving on then. We need to have a CH3 group that has how many neighbors? 0, because it shows up as a singlet. What's next to it? Can't necessarily say, but it doesn't have any hydrogens attached. And is this signal in the functional group region or functional group adjacent region? Kind of. According to our correlation table, this is kind of the borderline of alkane and functional group adjacent. If it is functional group adjacent, it's not close to a heteroatom functional group, because that, according to our correlation table, always sends it a little bit further to the left. And I want to remind you guys how to read this correlation table as best as possible, because there is some nuance to it. So on the right-hand side of the range are hydrogens that are adjacent to functional groups that are not very close to heteroatoms. Hydrogen, carbon, carbon, functional group. And on the left-hand side of the range, that's why this molecule is arranged this way. On the left-hand side of the range are signals from hydrogens that are closer to those heteroatom functional groups. Hydrogen, carbon, oxygen, rather than hydrogen, carbon, carbon, oxygen. Closer to an electronegative atom, more deshielded, shifted more to the left. So I don't know what's next to it, but it doesn't have any hydrogens, and it might be a functional group. And then my last one is a CH3 with how many neighbors? How do we know that? 3 peaks. 2 neighbors, so that's a CH2 group, which means this actually supports this structure and confirms that we don't have this structure on the bottom. Doesn't help me fill in much though. So I'm going to have to go back to relying on chemical shift a little bit more. So far, what we've analyzed, a CH2 with a CH3 neighbor and a CH3 with no neighbors. Those are both present here. CH3 with no neighbor, CH3 with no neighbor. CH2 with a CH3 neighbor, and a CH3 with a CH2 neighbor. So now there should be a difference in the chemical shift. Singlet CH3 bonded right next to the oxygen. Where should that show up? Further to the left in the functional group adjacent. CH2 adjacent to the carbonyl. Where should that show up? further to the right on the functional group adjacent. Versus CH2, directly adjacent to the oxygen. Signal should be further to the left. CH3, adjacent to the carbonyl. Signal should be further to the right. What do we see? Which of those two structural isomers matches this NMR best? A or B? Okay. Top one. CH3, further to the right, because it's close to the carbonyl. CH2, further to the left, because it's close to the oxygen. So if we were to label these signals A, B, C, from left to right, and then map them to our molecule, this is A, B, C. This compound doesn't work because the chemical shift for the 3H singlet is too low. If that singlet CH3 was closer to 4, that would be where I'd expect it to show up for this molecule. So the chemical shift is the only thing that we can actually use there to separate them.
Can you explain one more time, like how to like rank, like if they shift right or left?
Yes.
Like the priority, I guess.
No priority.
Okay.
No priority, unfortunately, but you can use this as a template.
Okay.
If the hydrogens are very close to an electronegative atom, it shifts the signal more to the left. If the hydrogens are not very close to an electronegative atom, or if they're just adjacent to an alkene, adjacent to an alkyne, adjacent to an aromatic ring, not a lot of heteroatom there, but there is a lot of, there is functionality. That functional group still de-shields it.
Okay.
So the closer you are to a functional group that is not very close to the heteroatom, more to the right. The closer you are to the heteroatom, more to the left. So that means hydrogens that are bonded near halogens, or a hydrogen bonded to the same carbon of an alkyl halide. Those hydrogens shift far to the left. This hydrogen's bonded to the same carbon as the oxygen. Maybe a way I can phrase this is when a hydrogen and a heteroatom share a carbon, the signal shifts further left. The hydrogen and the heteroatom share a carbon, the signal shifts further left. But when the hydrogen and the functional group share a carbon, yeah?
Mm-hmm.
When the hydrogen is bonded to the same carbon and a functional group is bonded to that carbon, further to the right. Functional group adjacent, unfortunately, is a really vague term, but that's because carbonyls don't always put things in the same place. Alcohols don't always put things in the same place. That's our compound right there. Let's prove it. I'll zoom out. CH3, signal B, CH2, signal A, CH3, signal C. This is ethyl acetate. Let's look at methyl methylpropanoate, which is that other molecule that we were looking at. The other structural isomer that we were debating. Yeah, I should just type in the chemical formula again. This website doesn't always do the best with names. got certain names in there and certain names it doesn't. Propionate. So I was very close. Let's look at this NMR signal. This NMR spectrum. What do we see? A singlet 3H further to the left. So those two signals that we were talking about, the ones that are both functional group adjacent, they just swapped places. That's all that happened. And the triplet CH3, still in the same place, because it's still more alkane in both of these molecules. And why don't we take a look again at the IR for this compound? Again, this was the compound whose IR we looked at on Tuesday. This compound's IR has sp3ch, CO double bond, and the CO single bond. We can't tell how this molecule is structured. We can only tell that it has the same bond types. Then, let's look at the other structural isomer. Oh, man. The other structural isomer that we were looking at, methoxyacetone. What do you notice here? The signals look a lot different from the last two NMR spectra. There's no doublets, triplets, quartets. They're all singlets. And that's because in methoxyacetone, the CH3 has no neighbors. The CH2 has no neighbors. This CH3 has no neighbors. But can we predict which signal is showing up where? Let's call these signals A, B, C from left to right on the NMR spectrum. Where is A on methoxyacetone? Here's A. Now I'm not giving you the integrations because I think that we can predict the integration based on the chemical shifts.
Would it be the furthest, like, right CH3?
A is this one?
Yeah.
So this CH3 is functional group adjacent, so I would expect it to be in a little bit further to the left of my functional group range.
Mm-hmm.
But what about this one? Isn't that also adjacent to the same functional group? Plus adjacent to this functional group? It's that compounding effect that the chemical shifts have. This CH2 is being pushed left by the deshielding of this functional group. It's also being pushed left by the deshielding from the carbonyl functional group. Does that make sense? Multiple groups adjacent to it, compounding effect. A integrates to 2H. Well, that tells us that B and C both integrate to 3H, so how can I predict which of those 3 H's belong to which side of the molecule? One is closer to the oxygen, one is closer to the carbonyl. According to the correlation table, closer to the oxygen is further to the left, which kind of goes back to what Brett just said, which was we should expect this to be further to the left. Yeah, thank you.
I thought I knew.
I know. Trying to break us.
Yeah, I'm not trying to break you. I have a question. If these two signals have the same integration, why are they not the same height? Because it doesn't matter. Height is not what we're going off of. It's the height to width ratio or product. It is the area that we're looking at. If this signal is shorter than this signal, but they have the same integration, that just means that this signal is wider than this signal, And I think that you can kind of see that. Again, this spectrum is not easy to interpret. It's a little grainy. But you can see pixel-wise that this is about 4 pixels wide, and this is about 2 pixels wide. It's a little bit wider. It's a little bit shorter. They have the same integration. All right, what do you guys think? Was that an interesting analysis of IR and NMR to deduce a chemical structure? We did it. We solved it. IR helped us narrow down all of the structural isomer possibilities. Well, first, degrees of unsaturation helped us narrow down what we could expect. Then, IR helped us narrow down structural isomer possibilities, helped us figure out what bonds must be present, what bonds cannot be present. NMR helped us confirm splitting patterns, chemical shifts, integrations. Okay, I plan to find a few more of these that we can do together, or at least one more of these that we can do together. But in the meantime, I did want to see if there were any questions that you guys have. Specific questions. I didn't actually get to read your email. Do you want to look at that one?
Sure.
All right.
Yeah, it was on, I believe, number 28 from the midterm practice exam.
Practice. Okay. Any homework problems that you guys want to go over? Any of the supplemental
23.
practice problems? Question 23. Okay, this is taking us away from NMR, but just for a minute, and I'm okay with that. Right? This is,
I'm guessing it would be a pretty short answer.
you're looking at the arrow pushing? Okay.
So I got like almost the exact right answer that I wrote in the box, but on the key, there's a lone pair written in on the nitrogen,
Okay.
but there's not a lone pair like in the original problem.
Yeah.
Why is there a lone pair in the product but not the
Yeah.
reactant?
Anybody want to take this one? Why did I draw a lone pair on the key in the product, even though there's no lone pair on the nitrogen in the starting material? Is it wrong? Is there not a lone pair on the nitrogen? Or is there a typo and there is supposed to be a lone pair on the nitrogen? It's implied. What did you say? There is a lone pair there, and it's implied. So part of bond line structure is that we can assume lone pairs. We cannot assume charges. And charges actually help us infer lone pairs. So the fact that nitrogen is neutral and has 3 bonds tells me that nitrogen does have a lone pair. And the fact that carbon is negatively charged and only has 3 bonds tells me that carbon also has a lone pair. In fact, that's the lone pair that is being indicated by the negative charge. That's the lone pair that is moving with the electron arrow. So hopefully when you saw this, just so that we look at the right answer together, when you saw this, you should see electrons moving from a bond to an atom. That means that that atom is going to take the electrons. Bond is breaking. Given that that atom already has 3 lone pairs, it's now going to have 4 plus a negative charge. Or I should say, it's now going to have 4, thus a negative charge. That is the charge that bromine has with 4 lone pairs. And here, a bond is forming to this carbon. So this CH3 will now be bonded to the carbon sharing its electrons. What's not happening, this carbon is not lobbing its electrons around, saying, I've got some, you can have it now, I'll just lose them. Atoms can lose electrons to another atom. Carbon has lost this bonding pair of electrons because bromine took it. It didn't just lose it to thin air. Or atoms can share electrons, but again, they can't lose it. So this carbon just shares with this methyl.
I think yesterday we talked about how like if there's an arrow from a bond to somewhere else where it's like a bond breaking, it's like safe to say that
Yeah.
like going from the negative to atom would be like a bond forming.
Yes.
Okay. it's
So
kind of-
starting from a bond going to an atom, you are showing a bond breaking. It can also be a bond forming if that arrow goes to another atom.
Mhm.
One example that I could give you is we're going to see this reaction in the second half of our semester. This is a bromination reaction. And it starts like this. 3 arrows all at once. I have an arrow starting at a bond. That bond is breaking. And the arrow is pointing to an atom. That bond is forming. One arrow that indicates both bond breaking and bond forming. Whereas here we have one arrow that only shows bond forming, one arrow that only shows bond breaking. Some arrows can do both. You okay with that?
For right now,
Yeah. And by the way, the products of this, another bromide, this looks exactly like what we see up there. Here, there's not a bond breaking because it's a lone pair, but it is a bond forming. So that's a carbon-carbon double bond goes down to a carbon-carbon single bond. Bond breaks. Carbon on the left, or let me say it this way. Carbon on the right accepts electrons from bromine, forms a bond. Carbon on the left donates electrons to bromine, forms a bond to bromine. Something's missing. So let me stutter and repeat my list. Something is missing from this. In the product. Huh? A charge is missing, not charge is. One charge is shown. Lone pairs can be implied. I don't have to show lone pairs. And I don't have my arrows either. Maybe that would help you distinguish what we're seeing. The starting materials are net neutral. The products are. I'm missing a positive charge because right now it's net negative. Where is the positive? Right? Bromine does not like to take on 2 bonds. It can, but it shares its electrons too much. That gives it a positive charge. So what we did was analyze the arrows as, are we seeing bond breaking or bond forming? Or both? Only bond breaking, only bond forming, both bond breaking and bond forming.
So is it really the only way to distinguish that just to make sure like the octet rules are satisfied, or?
That is a good way to do it. And some tips. Draw in your hydrogens. 2 hydrogens here, 2 hydrogens here, and in the product, I've got 2 hydrogens. A lot of times the errors with predicting the product from electron arrows is missing those assumed hydrogens and looking at them and saying, I don't know what else is there. Maybe the positive charge goes on that carbon. But if you have all of your hydrogens, it's a lot easier to pay attention to the octet rule. To bring this back to our conversation on spectroscopy, if I took this in a lab and I took spectral information, NMR, IR, mass spec, on the starting material and the product, which of those techniques that we've covered would help me experimentally distinguish my starting material from my product? How would I know that my reaction has gone to completion? NMR might be useful. These hydrogens should give a signal in the vanillic range, 4.5 to 6.5. And these hydrogens should give it more in the functional group adjacent range. So like maybe 4. So yeah, the chemical shift of the NMR should change. The integration would not. The splitting pattern would also change. How many signals here? Oh, actually, sorry, no, it wouldn't change. But how many signals would be produced by this molecule? Just one. All of those hydrogens are in an identical chemical environment. That molecule is very symmetric. How many signals would be produced here? Also one. Those hydrogens are all symmetric to each other as well. So I would still get just one signal with a singlet in both of the NMRs, but the chemical shift should change, so NMR would be useful. Would IR be useful? What change would we see in the IR?
See an alkene and then no alkene.
You gotta be more specific, because you can't see an alkene in the IR.
An sp2 to an sp3ch.
Good.
Start at
You would see sp2ch in the starting material. You would not see it in the product. You would see sp3ch in the product. You would not see it in the starting material. Now you said you'd see the alkene, but really you'd see the sp2ch. And if you saw the sp2ch, you'd also see, what's the corresponding peak for the alkene? There's literally only one other bond type in this molecule. Somebody say it. Say it wrong. What's the other bond type in this molecule that would show up in the IR? We saw the sp2ch. No halide. Okay, well, actually the Br2 molecule probably won't absorb in the IR. CC double bond. CC double bond. When you said we'll see an alkene, you won't. But you will see sp2ch above 3000, and you'll see CC double bond above 1600. That indicates the alkene. Although it also has some indication of an aromatic ring. It's hard to know the difference in the IR. You won't see an alkene. You will see those two bond types. In the product, CC double bond is gone. But you might see the CBr absorption. Although that only absorbs in the fingerprint, which makes it really challenging to actually label it. Okay, Rowan, you had a question earlier. Sorry. The arrow pushing or the
arrow pushing on the second example. Because the counting the charge at the end makes sense, but I don't quite understand where one of the electrons goes. Because to me it looks like the double bond is breaking, and
It
then
is.
that left carbon is sharing that pair with the bromine to form a bond.
Let me show all of the electrons then. So one bromine starts with 3 lone pairs, ends up with 4. That's because this bond was taken by that bromine. 2 electrons gives it its 4th lone pair.
Oh, I see what I.
Carbon-carbon double bond becomes a carbon-carbon single bond, so these electrons must be leaving the double bond to form a carbon-bromine bond. But this bromine started with 3 lone pairs and ends up with only 2. And we can know that by the formal charge. Do you guys remember that table we made week 1 or week 2? We looked at charges on our standard atoms, charge on carbon, charge on oxygen, nitrogen, halogens. The only time that bromine takes on a positive charge is when it has 2 lone pairs, 2 bonds. So where did that third lone pair go? It was used to create the other sigma bond. So the electrons are all there, but it does take some elaborating to see them all. Okay, shall we move back to spectroscopy, or do you guys feel strong enough on this that you want to just start your midterm review right now? Okay. All right, then let's maybe tell me, do you want this example where we take the NMR and the IR of a compound with its chemical formula and we derive the structure? Because it helps us kind of do everything at once, which is analyze IR, analyze NMR, and build a structure. Okay. I'm going to try to find one then. Oh. All right, I think what I'm going to do is take screenshots of the IR and the NMR, and I'll put them both up on the screen. And then we'll go through them together. Here's the chemical formula, though, so that you guys can get started. Because the first step should be calculate the degrees of unsaturation. Oh, hang on. So this is the chemical formula that we're working with. And here are the spectra. Sorry, your facial expression gave it all away. By the way, which one is IR? Which one is NMR? So you guys can tell the difference between these spectra by now. They all look really distinct from each other, and that's important. You can see at a first glance what information you're going to get out because you know the technique. I want to give you guys just a few minutes to look over these and see what you can get. By the way, I'm going to give you integration values without really trying to read redraw those signals. So we've got integration of 1H, 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 and 3H as you move from left to right. Yeah, maybe I can try to redraw. It's not really worth it.
Is it 3 equal to 0?
I'm sorry?
Is it 3 equal to 0?
It's for the one close to 2. The signal close to 2 ppm. I also will give you guys these lines at 3000. I'm just not sure if I can do it on this. It's so pretty. It'll look better on your unit test, I think. I'm actually gonna fill my water real quick, but if you guys want to, feel free to chat with one another about what you see in the spectrum. Really quite unexpected. I actually thought you guys would be like up and down. I think you're really close, but you might be a little confused about where you put this down. So just so you realize, this carbon has how many hydrogens? That's right. And then you have a 3H, 2H, 1H.
So you have 6H's total.
That's right, the chemical formula works, and this is not impossible. But I'm not sure if that's what you want. You're on a good track though. Okay. Mm-hmm. Well, you actually don't have enough H's. You got 1, 2, 3, 4, not 6. And I mean, you guessed there's an aldehyde, but is there any proof in the IR? Is there any proof in the NMR? Because the IR should show us that, and the NMR can give us some functional groups. Do we see any evidence of that? Well, the range here is from 10 or 9 to like 12. So if it's in that range, good. Okay, so use that as evidence then. Oh, that's not C. Nope. Nope. Use your NMR correlation table to help you assign that signal. Look at that range. That can push up. There you go, Cameron. You're onto something there. Not quite. What it's not going to give us is this signal in the NMR at 9.5. There's a couple of pieces in the IR as well, and it just doesn't quite verify.
Is that 3,000 line?
It's in the right place, it's just not very well drawn. But you're looking for a signal that doesn't seem to be there? Question mark? Yeah, isn't that the worst? But remember that some functional groups that show up in the IR also show up in the NMR. So you might be able to use both IR and NMR to help approximate some functional groups. Yeah? Do you see evidence of this? Yeah, I don't either. I mean, there's something up there, but it just doesn't look like what it normally does, which is very deep, very strong. And did you do the DOU calculation? Because that will give you some ideas of what you'll have to get in there. I would say that with what you're guessing right now, you're not aware. You're going to find out.
Was that the 15 marks where you go into left or right?
3,000 is where you tell the type of CH. 1,500 is where we don't need to analyze below 1,500 because it just gets a little too in-depth. Cameron, you want to talk with your neighbors and help them get to the same place as you? No, but close. No. This actually only produces 2 signals in the NMR.
So there should be like
4H, 2H.
What, like, I know how to calculate the degrees of unsaturation, but what is the significance of it again?
Degrees of unsaturation. And what it literally tells us is how much more saturated a molecule could be, how many more atoms total could be put on there, which really is a result of a pi bond or a ring. So if I have a ring, I could break one of those bonds, and each atom could then take one new atom themselves. So I could saturate the molecule with more atoms. If I had a pi bond, like what we just saw, I could break that pi bond between the two atoms, and each of them could bond to a new atom, each. And that would saturate the molecule more.
Okay.
So degrees of unsaturation tell us if we have pi bonds or rings, although it doesn't tell us which one we have.
Okay. And I also wanted to ask you really quick. So, we did this one before, like the ABC one.
Mm-hmm.
But you were saying like when H is attached to a functional group and they share a carbon, that would shift right. I know that there's no like shared hetero atoms in this one.
This oxygen would be, so signal B shares a carbon with a hetero atom. And signal A shares a carbon with a hetero atom and shares a carbon with a functional group.
Okay.
So remember that we're looking at the hydrogens. We're not looking at the carbons. What's producing a signal here is a hydrogen. So A in that molecule,
I get that it's like compounded, but I guess it was like because since it is attached to the functional group.
remember when I say shifts right or shifts left? What I mean is relative to this correlation table. Relative to this range on the correlation table. So this is where a hydrogen would show up if it was just alkane. But if the hydrogen shares a carbon with a functional group, it shifts it to the inside, or the right-hand side of this range. If a hydrogen shares a carbon with a heteroatom, its signal shifts to the far side of this range. If a hydrogen, like the one we were looking at before, shares a carbon with both a functional group, like the carbonyl, and a heteroatom, like the oxygen, then it shifts here, plus the amount that it would shift here, it shifts further than you would expect.
Okay.
It shifts left for its proximity to both of those groups.
Okay, so that's why it gets pushed left by both.
Gets
but
pushed left even further.
in
Yep.
retrospect of like the functional group, like just like closer in that specific range.
So we had one CH3 that was only next to the carbonyl, and it showed up furthest to the right.
Yeah.
We had one functional group that was only next to the oxygen. It showed up in the middle. And then we had one CH2 group that was both adjacent to the oxygen and adjacent to the carbonyl, and it showed up furthest to the left. Proximity to both of those groups shifted, compounding onto each other.
Okay.
You're not even done. That's not the right chemical formula.
I know.
Okay. Mm-hmm. Oh, that's okay. You got your DOU, which is great. Good job, Cordelia. Do you feel confident? Good. That's great. Michelle, how are you doing? Good. Aiden? You lean over their shoulders?
No, he's the smart one.
No, this isn't it. Notice that you have no hydrogen that produces a signal close to 10. The only thing that produces a signal close to 10 are these hydrogens.
Oh, so oh, I see.
Yeah, how would you know? I don't know. Oh yeah, maybe. That's a good idea actually. You could assume that, yeah. Yeah. Mm-hmm.
I forgot you could do that.
Should we tackle it together? What are the degrees of unsaturation? So, correct me if I'm wrong. It must have one bond, one ring. One pi bond, one ring. Oh, yeah. Or what? Oh, it could be two rings. Could be two pi bonds. Two pi bonds, that means it has to have a triple bond. Could be two double bonds. All we know is that there are 2 degrees of unsaturation, and there are several combinations for that. 2 double bonds, 1 triple bond, 2 rings, 1 ring, 1 pi bond. We're not sure. But now when we start looking at the IR, we can start looking for evidence of certain types of bonds. We can start looking for double bonds. We can look for triple bonds. Can't really look for rings. If we get more in depth, if we started learning how to analyze all of this in the fingerprint, we could start looking for rings, but we're not going to. Let's analyze the IR. Let's pull out key peaks, assign them to the bonds, because this is part of your short answer, part B, for your unit test this weekend. You will be given an IR, and you will be asked to report all of the bond types. And I want to make sure that you guys are on the same page with me about how you report a bond type. You don't look at a peak and say, that's an alkene. Because an alkene is not a bond type. An alkene is a bonding pattern, and it involves at least 2 atoms up to 3, the hydrogens and the 2 carbons. So let's look at the IR. I like to analyze the IR from the left high frequency to the right, because I'm only going to go down to 1500. And if we need to, we can identify peaks and leave them with question marks and try to use the NMR to help correlate. So I want you guys to walk me through this. I've done a lot of the talking. I want to hear from you. What do you see in the IR? What do you think about the peaks that you see from left to right? Brett?
I saw CO double bond.
Okay, so kind of skipping all of these, you came right here, which is great because this is the strongest peak in the signal. The strongest signal in the spectrum, strongest peak in the spectrum, which means it's probably meaningful. That shows up at 15, 16, 1700. So let's try and analyze this. 1700 wave numbers. Correlation table. Don't try and guess this stuff. Please don't. I'm going to zoom in on those that absorb in the 1700 region. What are you thinking? How would you maybe try to assign this?
Well, I don't know. My thought process was because there's like the thicker, longer signal, and then there's the smaller one right next to it. So there's also a CO double bond from 1615 to 1695, and then also from basically 1615 all the way up to 1820.
Yeah. So you think both of them could be CO double bonds?
That's what I was thinking, yes.
But our chemical formula only has 1 oxygen. So we'll only have 1 CO double bond, and it's only going to absorb once. Unless there were 2 carbonyls. The acid anhydride, for example, 2 carbonyls, has 2 absorptions. So I think one of those peaks is the CO double bond. One is something else. And given that this is sharper, stronger, this is likely the CO double bond. But can we assign a functional group to it? No. It falls in the range for ketones and aldehydes. It's not far from the range of esters and carboxylic acids. It's not far from the range of amides. So right now, do you want to just leave it at CO double bond? Valid.
With aldehyde, because there's also a mark at the 2800 mark.
Great idea. If this is the CO double bond of an aldehyde, we should see a corresponding peak. We also should see a corresponding peak if it's a carboxylic acid. And I think you guys know that those carboxylic acids look real ugly. And there's nothing ugly about this. So as you look at 2800, here's 3000, 29, 28, 27. I'm going to follow 28 and 27 all the way up. What do you notice? 2 peaks, twins, at 28 and 2700. That agrees with my correlation table. To give me what? No, not an aldehyde. The CH of an aldehyde. Thank you. Listen, I understand that you guys are going to be answering these questions using my correlation table. So you addressing that the signal at 28 and 2700 tells me an aldehyde. I know that you can read that it's a CH, but remember that you are listing the bond type. Aldehyde is not a bond type. Aldehyde is a grouping of bonds. This absorption comes from the bond type CH, but not just any CH, the CH of the aldehyde. Okay, well, that makes me feel a lot more confident that this is the CO double bond of the aldehyde. Although if you just put CO double bond there, I would accept it because, again, the only thing that confirms it is the corresponding peak here. What else do you guys see?
I see an sp2 carbon hydrogen bond.
sp2ch. Where do you see that absorbing?
I think the line is a little bit wrong,
Okay.
but it's between 3150 and 3000.
I agree. This line, a little messy, right? I couldn't give you a straight line, but I will on tests and on the exam. And I think there is a peak here to the left. And so we've got this absorption around 3000. Maybe it's a little bit above it, so I can say around 3010 wave numbers. I'm really just approximating. But if you said there's a peak between 3150 and 3000. Now, could Abram have told me, I see a signal above 3000, that's a CH bond? Because it's really meaningful that it's an sp2ch bond. It actually tells me there's another bond type I should be looking for, something that corresponds to an sp2 hybridized carbon. Hayden?
I was gonna say, like, past that 3000, there's like that broad stroke with that mini peak. Would that be carboxylic acid, or is it?
Here and here?
Like, is it still a part of that broad, or is it?
It's way too high of a region for the carboxylic acid. Carboxylic acid usually absorbs here.
Oh, okay.
And it's not intense enough. It's not strong. And it's not broad enough. I think what you're seeing is like this chunk here is all kind of low, but this isn't necessarily absorption so much as it is just experimental noise, if you will. But do you guys think that those two peaks, that kind of fatter one and the sharper one, do you think those are indicating bonds to us? Use the correlation table and let's look at what absorbs up there. Can it be an NH bond?
No.
Why not?
It's not a formula.
There's no nitrogen in the chemical formula. So definitely not an NH bond. Even though NH absorbs in that region, weak to medium, one peak or two peaks, but it's not. That, again, is just noise. It's an artifact that's not telling us anything. What about an OH bond? How many oxygens do you have? How do you already know that oxygen is being used? It's in a CO double bond. Can it also be an OH? No. So it's another artifact that's not telling us anything. Additionally, the OH bond, that's usually medium to strong, so that should be coming down a lot more than what we see, but always some hand waviness to this. Okay, so I'm not going to analyze those other two because I know it can't be an OH because it's a CO double bond. I know it's not an NH. Aaron?
Well, for the sp2 CH bond, you also have the sharp peak at 1680.
Okay, so here's that sharp peak. Who was mentioning that before? Brett, I think. This is around maybe 1620. I'm just approximating there, but again, you could put the range, 1680 to 1600, which indicates what bond type?
The double, the CC double bond of an
Alkene. Yeah. It's a little too high to be the CC double bond of the aromatic ring. We also don't have enough carbons for the aromatic ring. So the CC double bond of an alkene absorbing there at 1620. That's great. And that's what we call the corresponding peaks. I think that I have an alkene in this molecule. Those are the two peaks that correspond to it. I think that I have an aldehyde in this molecule. These are the two peaks that correspond to it. Is there any other significant absorption that we should recognize? Maddie?
I don't have another absorption, but one thing, like you were just talking about the aromatic ring.
Yeah.
Does that have to have 6 carbons in it?
For this class, the aromatic ring will have 6 carbons.
Okay.
When you get into OChem 2, you'll learn that aromatic is actually just an electronic property, and a lot of different rings can have that electronic property. But the template aromatic ring that we use in our class is benzene, the 6-membered ring, 3 alternating double bonds.
You're trying to draw like a smaller ring?
No, it wouldn't be an aromatic ring.
Yeah.
Mhm.
Okay. So we wouldn't, there isn't really anything we can see here that would prove that there is or is not like a small ring.
No, there's
Okay.
nothing that confirms or denies the existence of a small ring.
Mhm.
But we know there's 2 degrees of unsaturation. We identified a CO double bond, and we identified a CC double bond. We've used up our 2 degrees of unsaturation. No rings. There is one more absorption that I probably would take points off for if you didn't assign it on your unit test.
Is that a CO bond?
Nope, I wouldn't look for that because I asked you to analyze peaks above 1500. Good question. There might be a CO bond down there, but a lot of things absorb down there. And if there's only one oxygen and we have a CO double bond, I'm not necessarily looking for a CO single bond. There is a signal to the right of 3000, which is meaningful. That's the sp3ch. 3000. I mean, it doesn't go all the way down to 2800. It's like it stops at 2850 wave numbers. Okay, so on your unit test this weekend, one part of your short answer is take this IR and assign all of the major key peaks. I want to say I did phrase it a little bit differently so that you could miss 1 or 2 without losing points. I want to say that I phrased it as like identify at least 2 key peaks above 1500. But it's going to help you the best if you identify as many as possible. What do you guys think about analyzing the IR? Do you think we've got everything? 5 signals, not bad. 2 functional groups, pretty good. We've got an aldehyde and an alkene in here. So coming back to the NMR, we've got a signal close to 10, integrates to 1, signal around 7, integrates to 1, signal around 6, integrates to 1, signal around 2, integrates to 3H. Hayden.
I think like the most confusing thing for me at least is like on the left, that left data graph. How do you know there's 3 H's on that 2 BPM? It's like I counted.
I tell you.
Oh, okay.
You would need to integrate. You need to have your computer integrate this signal and give you the area underneath it. Obviously, you can't integrate it. I'm not letting you bring your computer into the exam to integrate it. So I will give you the integration above the signal. 3H.
So I remember we were counting the 1 H, 3 H's though. What was the difference?
Peaks tell you how many neighboring hydrogens that hydrogen has. So hydrogens are making these signals. Neighboring hydrogens are changing the peaks on the signals. Hydrogens make these signals, and their integrations tell you how many hydrogens make that signal. The splitting pattern, the multiplicity, is affected by the neighboring hydrogens. And this is a confusing part, so I want to say it one more time. Integration tells you how many hydrogens make the signal. Neighboring hydrogens determine the peaks of that signal. So you want to think about splitting pattern, peaks, and integration differently. They tell you two separate things about a molecule. Does the NMR help you confirm any functional groups? Tell me. The NMR helps you confirm the aldehyde? Really? How would it do that? Sorry? I've got a signal at 9.5, and there are only two types of hydrogens that our correlation table predicts to have signals all the way up that high. Carboxylic acids and aldehydes. And if you remember, the correlation table is laid out so that you think things that are more on the right produce signals more to the right, like the aldehyde. Its signal will be closer to the 9 to 10.5 region. Carboxylic acids closer to the 10.5 to 12 region, but could be anywhere in there. I have a signal up that high, which tells me I should be expecting the aldehyde to be there. So I'm going to start with this. I've got an aldehyde in my structure, confirmed. That is signal A. What else?
We have two vanillic.
2 vanillic. Is it really vanillic though? Because when we look at our vanillic region, okay, yeah, the vanillic region kind of goes from 4.5 to 6.5, 7-ish. But it's also butting up into the aryl region. So how would you know it's an alkene, vanillic? How do you know it's not aryl, an aromatic ring? Not enough carbons for the aromatic ring. And we understand that the chemical shifts are compounded by being in different groups, like perhaps an alkene hydrogen also being adjacent to a carbonyl. That's going to shift its signal even further to the left. So 2 vanillic hydrogens. Can we say for certainty, let's say 1, 2, 3, 4. Can we say for certain whether the alkene is here, here, or here?
It can't be that.
Can't be here. It would break the octet, or it would remove our aldehyde hydrogen. So it cannot be here. How would we know whether it's between these carbons?
You got 3H.
Okay. Well, if the double bond is here, I still have an sp3CH. If the double bond is here, I still have an sp3CH. If the double bond is here, I get 1, 2, 3 vanillic hydrogens, a CH2 at the end. And if my double bond is here, I only get 1, 2, plus a CH3, or if it's here again, I get a CH2. And my integrations tell me I need to have a CH3. CH3 is only going to show up at the methyl group. So I cannot put a double bond there. I can't get rid of that methyl group. I can only put a double bond there. Now, I wouldn't make you assign those signals, but I think we can make a pretty good guess. This signal that is further to the left is probably closer to the aldehyde. Further to the right, further from the aldehyde. But, you know, it's a little confusing, a little trippy in there, not the learning objective. And then the CH3 confirms that. Sorry?
If you, in the color test, if you enable them like 5 to what like 2 points off.
No, you do not have to do this labeling on the test.
Oh.
No. But this is just our way of confirming the integrations match up. Okay, what do you guys think? Can you predict a molecular ion for that compound? We're not looking at its mass spectrum, but could you predict a molecular ion for that spectrum? Looking at the mass spectrum doesn't tell you anything that you need to know about a molecular ion. Anybody?
I'll do it.
Yeah? Draw a plausible molecular ion for this compound. What do you guys think? Thank you.
Yeah.
We can fix it if we need to. Would you accept this as a plausible molecular ion for this trans 2-butanal? Why not?
It's a potential ion, but not a molecular ion.
Okay. Double bonds can still be there. There are ways to make molecular ions without changing any of the double bonds. Does it look to you like this and this are connected? Are they? Did you mean for this carbon and this carbon to still be bonded, or did you show two fragments?
Oh, yeah, 2 fragments.
Is a fragmented molecule going to have the mass of the molecule? Which of these fragments hits the detector? This produces a signal. This does not. This would give us the M-15 signal because it loses a methyl group. So, not a plausible molecular ion. Thank you, though. Anybody else? Aiden?
I was gonna ask you, like, if this were to be like plausible, like if the aldehyde didn't exist, the double bonds would the resonance like draw it out to go to the lone pair, or would you just draw it out with the double bond still there? Because you mentioned that double bonds can still stay there, but I thought they would have to jump up to the lone pair. It's
Yeah, you know what? I don't think I'm catching what you're stepping in.
yeah. So like that CH is double bonded, right?
Yeah.
And I remember you mentioned like sometimes the double bonds can stay there even when radical is elsewhere.
Yeah.
But it's like since that CH, that methyl, it's there's a double bond right there. Wouldn't it just go up there and then just put a lone pair on top and the other double bonds go there?
Well, positive charges can't go anywhere because positive charges are holes. They are the lack of something. Electrons would need to come down to this, but oxygen is not going to give its electrons away. It's not going to let carbon take the electrons and do anything with them. We can talk more about that later, but no, I don't think what you're thinking is right. Anybody else think they can show a molecular ion? How many correct answers are there for this? Maybe two minimum. I can think of at least 3 very distinct, up to like 8, 20. Not 8, I meant 20.
So that double bond goes away, so it has a net positive charge.
Where? Sure. And what is a molecular ion? It's also called a radical cation. So where's your radical?
Would just have the other side where the bond was.
Yes, good. All right, what do you guys think? Is Cameron's a molecular ion? No fragments were lost. No little methyl radicals kicked off. The easiest way to form a molecular ion is not to break a sigma bond, which really causes fragmentation easily, but to break a pi bond. Removing one electron, one carbon gets to keep the radical, one carbon loses both of them. So this is plausible, so is the option where the radical and the positive charge flip. Any others?
So was the first one an example of alpha cleavage?
Yeah, that would be an example of an alpha cleavage. Good catch. What do you guys think about Maddie's? Plausible molecular ion? She didn't take out a pi bond. She took a lone pair electron. And since oxygen had the lone pairs, it still keeps the remaining electron from that lone pair as the radical, but it also takes on the positive charge. When a pi bond breaks, one atom takes a positive, one atom takes a radical. When a lone pair breaks, the same atom takes on the positive and the radical. Great work, guys. These would both be plausible molecular ions for this. What we have just done was taken an IR and an NMR for an unknown compound. Given its chemical formula, we identified all of the major bond types, which helped us predict functionality. We used NMR to actually confirm some of that functionality. And then we used NMR to confirm the structure. And once we had the structure, we predicted molecular ions. That's your unit test this weekend. No tricks. Those 3, 4 things. Abram.
So if you wanted us to predict a fragmented one, you'd say fragment or alpha
Well,
cleavage?
I would probably say, if anything, I would say predict the structure that forms the base peak. That's not always straightforward. To me, that's a little bit beyond the scope of our class. I want you to be able to recognize cations make signals, whether that's the molecular ion or a daughter ion. But I want you to be able to predict molecular ions and how they form.
I just wanted to go with the NMR on there again. The 2 hydrogens, the 2 sp2, the hydrogens that are bonded to the double bonding carbons.
The vanillic hydrogens. Yep.
They have like way more peaks than you'd expect. Is that
Totally.
just an artifact?
Do you remember yesterday when we were talking about NMR splitting patterns and I said, don't try to use NMR splitting patterns for alkenes or aromatic rings. They just get way more complicated than you'd think. In fact, I truly believe that splitting pattern for the purposes of our class are actually some of the least useful information. If you have a small molecule, you can usually figure out what's correct by the integrations and stuff like that. Do you know what I want to revisit with you guys is an odd aspect of OH and NH bonds in the NMR. So this is a compound called diethylamine. Well, that's not fair. They, sorry. I guess they don't have the NMR for it. I should be able to give you this. This is a compound that has an NH bond. That hydrogen shows up in the NMR. It's a hydrogen. But the hydrogen doesn't count as a neighbor to the hydrogens on carbons, and it doesn't get split by hydrogens on carbons. It does not count with multiplicity. Multiplicity is a communication of hydrogens through a carbon chain. Heteroatoms block that. And you might also think, oh, this is not a hydrogen that shares a carbon with a heteroatom. This is a hydrogen that shares a carbon with a heteroatom. This is a hydrogen that shares a carbon with a heteroatom. Those signals we know shift pretty far left. But what about the hydrogen that is bonded to the heteroatom? Shouldn't that be like at the end of the spectrum? Right here, the NH hydrogen, right at 2. Why? Mostly because of hydrogen bonding. The molecules in this sample being analyzed are hydrogen bonding with each other. So yes, the nitrogen is de-shielding the hydrogen. But another molecule's nitrogen is sharing electrons with that hydrogen through hydrogen bonding, re-shielding it. So signals of OH and NH do not show up as far left as you might expect them, but they always show up as singlets. They sometimes show up broad because of that hydrogen bonding. The hydrogen bonding changes the nature of the bond, nature of the hydrogen's environment, so it gives off kind of a wider signal, more characteristic. I wanted to talk about that. The last thing I wanted to talk about, you're not going to see carbon NMR on your unit test or on the exam, but carbon NMR is actually a little bit easier to interpret than hydrogen NMR. There's never any splitting patterns. Their coupling is just too weak. And the height more accurately represents the integration because they don't split. And it's the same issue where the more de-shielded a carbon nucleus is, the further left its signal goes. So the signal from carboxylic acids, aldehydes, ketones, alcohols, alkenes, amines, they kind of have those characteristic regions as well. And you'll notice the chemical shift. This is 0 to 10. That's where we find hydrogen signals. And about 20 is where you start seeing carbon signals, all the way up to 200. We're not going to spend much time with them, but if you can understand hydrogen NMR, carbon NMR will feel like a breeze. All right, this weekend, unit test, opens tomorrow, closes Monday night. Tuesday morning, the review unit test opens, just for the one day before your midterm. So you can go in and get extra practice problems from the unit tests. Tuesday, review day. We can review spectroscopy, but I find that most of the time, students want to review units 1 and 2 because they just got all the answers they need for unit 3. So come in with questions on Tuesday. Do you want to look more at arrows, formal charges, resonance, etc.? Come in with questions and we'll spend our time as wisely as possible. Have a good weekend, guys. Happy studying.
For the one that I drew, would that be like what we were doing like yesterday in lab, and it was like, and this one predicts?
Yes,
I
you're
was
exactly
like,
right.
I was like, I understand. I was
You drew a plausible daughter ion.
okay.
Possibly the base peak. I didn't actually look. The base peak is at, oh, this isn't the same molecule anymore.
Is that 49?
Yeah, basically.
49.
I don't think
49.
that was it, but.
I think I.
So that was a loss of 29.
Actually, yeah, I dropped.
And a loss of 29 would probably be 15 and 13 is,
It's just cleaving the aldehyde.
oh, yeah, okay.
Well, that's what I did.
What would that weigh? 16, 12, and 1, 29. Okay, yeah.
So